A small airplane has wings that each have a surface area of 9.0 meters squared, and they're designed in such a way that the air across the top of the wing has a speed of 50 meters per second, but going underneath each wing at the bottom, the airspeed is just 40 meters per second, and that leads to a pressure difference between the top and bottom of the wings, which leads to an upward lift force that helps keep the plane in the air. And it gives you, in this problem, the density of the air, which is 1.2 kilograms per meter cubed. So in part A, you just want to find what is the pressure difference between the top and bottom of the wing. So if I draw a front view of this wing and label the bottom of the wing as region 1 and the top of the wing as region 2, I can set up Bernoulli's equation to find the pressure difference. So Bernoulli's equation was the P1 plus 1/2 rho V1 squared plus rho G H1 equals P2 plus 1/2 rho V2 squared plus rho G H2. There's one thing that we can cancel out from both sides of this equation, and that is the height. Because if you consider the height of the bottom of the wing from ground level as being H1, and then to the top of the wing from ground level as being H2, there's practically no difference between those heights. It's going to be so negligible that we can basically just ignore it. So I'm going to cross out the rho g H1 with the rho g H2 on both sides of the equation and just be left with an equation that relates the pressure with the velocities. We're trying to find the pressure difference, which is P1 minus P2. So I'm going to bring the P2 over to this side of the equation and bring the 1/2 rho V1 squared over to that side of the equation. So that gives you P1 minus P2 is equal to 1/2 rho, and I'll factor out the 1/2 rho, so you end up with V2 squared minus V1 squared. So that pressure difference is equal to 1/2 times 1.2 times V2, that's the speed at the top of the wing, which was 50 squared, minus V1, the speed at the bottom of the wing, which was 40, that's squared, and that gives you a pressure difference equal to 540 pascals. So the pressure at the bottom of the wing is greater. P1 has to be greater than P2 because we ended up with a positive answer, which means that the pressure at the bottom of the wing, which is an upward pressure because it acts perpendicular to the wing, is greater than the downward pressure on top of the wing. So that net upward pressure, the net upward force, is what leads to the lift force on the wing. So in part B, let's figure out what the upward lift force is. And this just comes from the equation that pressure is equal to force over area. So the force, in this case the lift force, is just equal to pressure times area. And we're looking at the pressure difference, which was the 540 times the area of the wings. We have wings that have an area of 9 meters squared, and there's two of them, so we got to do 540 times 9 times 2, leading you to an upward lift force of 9,720 newtons. And for part C, if there's no other lift on the plane, what would be the mass of the plane? So if you think of a very simple free body diagram, we can just draw a dot to represent that plane, and then we can say that it has the downward force of gravity and the upward lift force, and since the plane is not accelerating up or down, we can just say those two are equal to each other. So the lift force was the 9720, so when I set them equal, I can just say replace the Fg with m times g, so FL equals mg, and then just divide both sides of the equation by g to get the mass. So the mass of the plane would be the lift force, 9,720, divided by g, which is 9.8, and that gives you a mass of 992 kilograms.